Lesson 23, we're back to ellipses. Now, remember I said we were going to skip number 7 and we're going to jump straight to number 9. So we're looking at standard forms of equations of an ellipse with a center at any generic point h comma k. Okay, looking at the center h comma k. With this, if I changed h and k to be 0, 0, then I would be back at the origin. You can fill in all the information for the standard form of the equation at the origin on that table if you'd like to. But what I'm going to do is I'm going to go ahead and assume that we have some ellipse centered somewhere other than the origin. I'll place it over here. That's a value of h. We'll put this value of k here. Now, what I'm going to do is I'm going to draw an ellipse that has that center to the best of my ability so that it looks nice and accurate. Okay? Now, if I'm playing with something that looks like this, there's my ellipse. I'm going to have 2 points, one here and one here. Those ones are going to be considered the foci. Okay? So those are the points where, again, the thing rotates around those values. Now, the points on the end, here and here, those would be considered my, my vertices. Now, this particular point is going to have a value on it. And now I'm kind of going backwards from what I would generally do, and that would be generally pointing out the equation, manipulating it appropriately, and then getting to the values. But what I'm going to do is I'm going to talk about this being h comma k. I'm going to move my value to the center, and then I'm going to add a value to it based on the major axes. Again, this being the major axis, I'm going to add a value to it. What value is that going to be? Well, based on the way we want to set up this equation, that's going to be h plus an x value shift, right? We're going to go over here in terms of x instead. Now, that's going to be plus an a comma k. Likewise, I'm going to have this point over here, and that point's going to be over to h. Now I'm going to subtract the a comma k. So that vertex is going to be h minus a comma k. Now, if I wanted to find the ends of the minor axis, which actually they will never ask that you do, okay? But there are points up here and down here which we could find if we needed to. Now, finding those points is actually very helpful for us, or at least knowing where they are if I wanted to graph this ellipse. Those points, again, they're not vertices. These 2 points are not vertices. It's only these 2 points that are vertices. This point here is going to be over to h. We're going to go up to k, and then I'm going to add a value to it up here. That value that I'm going to add is k plus b. Okay. Likewise, down here, it's going to be h comma k minus b. Now, the foci, the points in the center, those are going to have a specific value as well. They're going to go over to h, up to k. But now I'm moving in the x direction again, so it's h, and this is plus, we're going to call it c, comma, k. This one over here is h minus c, comma, k. So, all this information, let me write it down, and we can fill in the coordinates of the vertices and the foci right now, okay? So that's what we're going to do. We have the vertices. The vertices are going to be h minus a, comma, k, and h plus a, comma, k. The foci are going to be the h plus, plus c, comma, k, and h minus c, comma, k. Okay, now, it's a matter of knowing what the c value is, knowing what the a value is as well. Well, let's go ahead and talk about the length of the major axes as well as the minor. The length of the major axis is actually 2a. Again, notice from a negatively to a. Those values, if I ignore the fact that we shifted, is going to be 2a. The minor axis, on the other hand, however, is actually 2b. Again, the length of this line here, passing through from this point to this point. Now, with all this information, what equation would satisfy all this information and still satisfy the concept of from the foci to the ellipse, I'm going to have those two distances added together. It'll always be the same number. Well, the equation for that is this. Okay, just like in the last video, we had x squared over a squared plus y squared over b squared is equal to a constant 1. Well, now, if I want to shift these values around, I'm going to have x minus h squared divided by a squared plus y minus k squared over b squared equals to 1. Now, this requires a specific situation. Okay, the situation it requires is the fact that a is greater than b. If A is greater than B, then I do have my major axes here. What happens if in this equation we swap these two terms? Well, then I'm actually just going to have the equation where my major axes, because A is still going to be greater than B, and A would be under the Y value, I'd have the major axes go this way. So it would actually be longer this way. Again, notice the comparison of what I'm apparently drawing to what's already drawn. This is the x-axis being major. This is the y-axis being major. So, all of this information, along with the concept, lastly, that I'm going to have the rule. Now, this is a rule for all ellipses that sit in a specific form. Okay, and that form is this: c squared is equal to a squared minus b squared. Again, given this information, given all this information, the c value, if I'm giving you this equation, you can find me the position of the foci, finding out what that c value is by using this formula. Now notice this formula is not the Pythagorean theorem. It is slightly different. It has a comparison that if you wanted to see the Pythagorean theorem, it'd be b squared plus c squared. B squared plus c squared is equal to a squared, which again is not the Pythagorean theorem. Do not confuse this with the Pythagorean theorem. A way to help us remember it is that if I have the plus sign between these two situations, I'm going to have a minus sign in this formula. This is actually going to swap when we look at a different type of conic. So, this is all of the equation rules that we're going to play with. Whenever you're working with these things, this is what we're going to play with. Now, what if I were to change my A location? Now, this is still implying that A is greater than B. Keep that in mind, that this is still implying that A is greater than B. So, I have this occurring for the equation where A is greater than B. That means that the value under y squared, is actually the value that's larger. So now, this one here corresponds to the graph that you have in this top corner. This one here corresponds to this graph. With this information, okay, we're still going to have our c squared is equal to a squared minus b squared. But our values that are going to be added to these pieces, or the way that this graph is going to look, is going to be more like this. And I am exaggerating what a foci or what an ellipse might look like in terms of this situation. Now, our vertices are going to be where? Our vertices are going to be here and here. Notice the addition values that we're going to have are going to be in the vertical sense, in the y-axis sense. So now instead of having h minus a and h plus a, we're actually going to keep the h constant, and it's going to be k plus a and k minus a. Okay? Lastly, in terms of the foci, the major axes and the minor axes, you're going to have the foci are going to be here and here, again, in terms of a change in the vertical axis. That means that it's going to be an h comma k plus c and h comma k minus c. Notice it really just comes down to being able to find what the a value is. Is this one larger, the one division in terms of the k, or sorry, in terms of the y, or the one in the terms of division in terms of x, like we would have up here? If the larger division is in terms of y, then that's where my axis is going to be exaggerated most. If the larger number is in terms of the division of b, then I'm going to have it going this way in this situation. Again, notice these are two different equations where we have a and b different values. This is just corresponding to the fact that we have a and b, a always being larger than b. Okay, so if a is larger than b, this is what I'm going to work with. I'm going to take the larger number minus the smaller number. That's going to be my c squared, and I will be able to find out what my foci are. Now, major and minor axes, in terms of these situations, are actually going to be the same. Because the major axis is the a value is the larger one always, I have 2a for my major and 2b for my minor. Now, this actually covers all of the rules that we would need for the ellipse. And if I can find my formula sheet, you'll see here, in terms of ellipse, we have the parabola right up here. The ellipse actually has the same information. A squared under x, my major is a or 2a, my length of my minor is 2b, and I'm changing the vertices in terms of the x-coordinate by a, and my foci, the x-coordinate by c. And we still have this rule right here. Notice over here where I have my a value is under the y, and the a is supposed to still be larger than b. This is all true. Yes, you will get this in class. Okay, but this is the formula sheet in terms of ellipses, parabolas, hyperbolas, which we'll get to here soon. Now, with that being said, what I'm going to do is I'm going to go through in the next video all of the examples that we should be able to play with.